Hello everyone and welcome to another solutions video today for round 763. This was a pretty good round, I would say. Some implementation based problems and some nice problems as well. And let's discuss the solutions. I was not able to solve D. I think very close, but I wasn't able to solve it. So I'll only discuss A, B and C. That being said, let's begin and make sure to subscribe. Okay, so in this first problem, we have a grid. So we have an n by m grid. Okay, so we have a grid like this, and we are at some place, let's say here. So we are at source, and there is garbage somewhere around here, let's say here. And this robot, okay, it's not us, it's a robot. This robot will move +1 in the x direction and +1 in the y direction at every step and clean anything that is sharing the column or the row with it. So basically, currently it is at this position, right? So it will clean anything that comes in this column and in this row, but the garbage is not there, so it won't get cleaned. Anyways, in the next step, it will move like this. It will move like this here and then clean this row. So sorry, this column and this row. But again, didn't get cleaned. So after that, okay, let's say x was not here, but it was here. So after that, it will move again, and again it will clean this row, this column in this row. Garbage doesn't get cleaned. And then, as you can see, it cannot move down anymore, so it will start moving up. Basically, its velocity in y direction gets multiplied by -1. So, but the velocity in x direction remains same. So it moves 1 in the x and 1 in the y, but this time opposite. So it goes here. So that's the resultant. It goes here, and now it will clean this column and this row, and the garbage will get cleaned. So we want to tell the number of steps. So as you can see, we can just simulate this process and figure out when we will clean it. Reason being, n and m, they are 100, right? So n and m are 100 and t is 1e4. So we will eventually clean it. And why it will happen, the reason is, see, I'm claiming that it will happen in O maximum n comma m, and the reason is, if you observe its trajectory, right, you will notice that, let's say if we start from here, let me use a different color. If I start from here, I go something like this and then this. As you can see, I have covered every row. And if I were to start from, let's say here, right, then I would go like this and this, and here, as you can see, I've covered every column. So in minimum O and m steps, we either cover all the rows or all the columns. So that is why we can safely simulate it, and it would take about 100 operations per test case, and there are 10 to the power 4 test case. So 10 to the power 6 overall number of operations approximately. So that fits. Now let's have a look at the implementation. Zoom in more. So this is my implementation. First of all, I take everything input. N, M, Ij is the position, and Ti, Tj is target I, target j. So Di, Dj is the delta I, or velocity in I and velocity in j, and answer is the number of steps. So I am able to clean the garbage when either the row or the column matches, right? And if both matches, then also. So as long as this does not happen, as long as either my current row and my current column does not belong to the row and column of the garbage, what I will do is I will say I plus equals to di and j plus equals to dj and increase the number of steps we have taken. But before that, I'm also doing this, and this is to check. Okay, now here as you can see, if I add di and I will get greater than n or less than 1, that is I go out of bounds, then that means I want to reverse the direction. And similarly for j, and here the bounds is m and 1. So this was the implementation for a. Pretty simple, I think. But yeah, it required a little bit of thinking. Okay, so second problem, game on ranges. This was an interesting problem, I guess. So in this problem, we have a range of 1 to n. Okay, Alice has a range, and then Alice will, so initially Alice has only one range, but later she will have more ranges. So what's happening is at each step Alice chooses one of her current ranges. So in the first step there's only one range, so she chooses this, and then Bob will choose a number, let's say x, and what will happen is this will get divided around x. So this range becomes 1 to x minus 1 and x plus 1 to n. So now as you can see, there are two ranges and Alice can choose either of them, and this will keep happening for how many steps? N steps, right? Because at every step one number is being eliminated, so after n steps the set will become empty. So okay, this is I think wrong notation. I should just say phi, the empty set. Okay, so we have this, and what we want to do is, so in this problem we are given all the ranges that Alice selected at some point. It can be at any point, and what we want to do is we want to tell that for whatever range the Alice selected, which we have, right, we want to tell what number did Bob choose. So how to do that? Okay, so now let's take an example. So let's take an example of 1 to 5. If I, let's say, choose 3, right, then it becomes 1 to 2 and 4 to 5. Then if I were to choose 2, then it becomes 1, right? And then if I were to choose 1, it becomes empty. And if I were to choose 4 instead of 2, I would get like 5. And then if I were to choose 5, this. So as you can see here, the number of ranges that covered 3 was only 1. And the number of ranges that covered 2 after removing this. So after removing this, the number of ranges that covered 2 was only 1, right? This range covered 2. And then after removing this range as well, the number of ranges that covered 1 was 1. And similarly, number of ranges that covered 4 after removing this one is 1, right? So I remove this, and then the number of ranges that covered 5 is 1. So this is just an interesting observation. I'm sure there are other ways to approach constructing its solution, but for my solution, this was my observation, that at every step some number is being eliminated, and that is its last occurrence. So it's pretty obvious, right? And so how do I use this? Let me show you with the implementation. That would be more easy to understand. So here what I'm doing, first of all, I have the set of ranges that Alice at some point selected. So I input them, and then I iterate through all the points which are 1 to n, right? And then I count how many ranges were containing that point. So because I needed to see, right, 3 was contained by only one single point, right? And using this information, I will be able to calculate what 3 was, right? I mean, what the first number that was selected was. The number that will have its frequency 1 will be the number that was selected first. And then the number which will have frequency 2 will be here. And then the numbers which will have frequency 3 will be here. and so on. So that is why I am storing two things. First of all is the frequency for every number, and the opposite. So for example, frequency of let's say 1 was 2, of 2 was let's say 3, and of let's forget this example, let's take this example only. So frequency of 3 was 1, of 1, 2, 4 and 5 was 2, right? No, oops. So of 2 and 4 it was 2. So this is the numbers and this is the frequency, and frequency for 1 and 5 was 3. So that's what I'm storing. For every number I'm storing its frequency, and this thing is storing the numbers which have frequency I. So ci count I, so it will be a vector because many numbers can have same frequency. And now I will do the construction. So I will start from frequency 1 up to n, and for every frequency I will get some number. Okay, it doesn't matter, I can do it in any order. As you can see, this one, so this thing, this range operations and this range operations, they are pretty detached, so we can process anything first. So that's what I do. First of all, I take out some value current, and then what I see is I try to find a range that has it. Okay, so I try to find a range that has it using this for loop, and because n is just 1e3, I can do this n square loop, and whenever I find that, I'm saving it into x, and now I know that this number which was current, right? So this number current was contained in this range x, so I'm printing that, and then I'm removing this. Now this is crucial for the implementation, because now look at it from the first step. In the first step, we will see which number has the frequency 1, that is 3, right? So we have 3. Now we will check which range has 3. Only this range has 3, right? So I will get this range, and now I will do for the number with frequency 2. But here notice that 2 is present in 2 ranges. So how do I ignore this range? That's right, by deleting it, because this has been processed. So for the range 1, 5, I had the number 3, and now when I'm processing number 2, right? When I'm processing number 2, I see that only this range has it. And since only this range has it, I will print this range with this number. And then I will print this range with this number. And that's what's happening here. And after everything, I just print another new line. So yeah, this was also a decent implementation problem. I'm sure there are other ways to do it, but that's what my solution relied on, and I think it was pretty neat. That's why I'm showing that only. And now the third problem which I was able to solve, and this was a good problem. So in this problem, we have heaps, okay, heaps of stones. There are n heaps of stones, and what we are doing is we are doing an operation for heap 3 to n, okay, from 3 to n. So in this range we are doing the operation, and first of all we will do that operation on 3, then 4, then 5, and then up, and then in the end on n. Okay, and what that operation is, you take something like, so let's say it is like this. Okay, so you take some value out of it, so some stones from this. So let's say you take out 6 stones, and then you divide it by 3. So that's why you need something that is divisible by 3. So you take some number of stones that is divisible by 3, that is 6. We divide it by 3, we get 2, right? So we transfer 2 stones to the heap that is just before it. So plus 2 here and plus 4 here. So we took out 3 times 2 stones from this heap. We transferred plus 2 heaps to I minus 1 heap, if this is I, and plus 2 times 2 stones to the I minus 2 heap. So that's what we are doing in every operation. And what we want to do, what we want to calculate is, we want to calculate after doing this operation in some way. Now we are choosing this x, right? That this number 6 we are choosing. We are choosing how many stones we want to transfer. So we want to choose these stones in such a way that the minimum number of stones in any heap is maximized, and we don't want to tell what is the order of operations or anything. We just want to tell what is the maximum value of the minimum number of stones in heaps. Okay, so we want to calculate the maximum value for the minimum number of stones in the heap after doing this operation, this sequence of operation. So this, whenever you have to do something like, maximize some single digit value, right? In this case we want to maximize the minimum among all the heaps, right? We want to maximize this particular value, right? Whenever we want to maximize a single value or minimize, what we can do is we can try to see if we can binary search, right? This is called binary searching on answer. It is pretty common method. So let's see if it is even possible to do so. So let's say I want to check if I can get every heap to be greater than equals to x, right? So I want to find some way of doing these operations such that it is optimal for making every heap greater than equals to x. Now what does optimal mean here is not that we want the minimum to be maximum. No, we just want minimum to be greater than equals to x. Okay, so there can be multiple ways to do it, but we want to find one general way which will always be optimal enough. So let's see how we can do it. So let's draw it like this array. And okay, so we have h1, h2, h3, h4, hn, and we go from h3 to hn, right? Now since we want to check for greater than equals to x, right? Then when we are performing operation at h3, what we can do is we can transfer h3 minus x amount of stones using the operation to the previous ones, because so the previous ones could have already have more than enough, right? But just to be on the safe side, we will transfer as many as we can, because this will remain greater than equals to x, so we don't care, and this will be always good enough, right? Because we are doing the transfer whenever we can. Now this is not the perfectly correct optimal strategy. Let me tell you why. Because what if this has only 3 but this has 10 and this is like 2 and 2? Now we cannot really transfer, and we want to, let's say, check for 3, right? So we will see that we cannot really transfer everything here. We will, but what we can do is wait, yes, so what we can do here is see, using our current strategy, we are calculating this value to be 0 and we are concluding that no transfer can happen. However, what we can do is we can first of all transfer all of this. So we will get something like this. So 430 and then 10, and then in the next step we will transfer again. So we will get like so 3 plus 6, sorry, let's say it's 20. Okay, so 20 minus 9, 11. So this becomes 3 and this becomes 3 plus 6, so 9. So as you can see, we can move this. We can move more than h3 minus x using the help of the succeeding operations. So how do we calculate it? Well, what if we change the order of operation? What if we change the order of operation like this? First of all, we try hn, because see, hn won't be receiving stones from anyone, right? h3 here was gonna be receiving stones from h4 and h5, but hn won't receive. So for that this is the maximum stones hn can transfer. So first of all, we calculate that, and then we calculate for this, right? For hn minus 1, then for hn minus 2, and so on, right? That makes sense? Yes, we are almost to the correct approach. Now here's a problem, and the problem is that it was like 2 2. Let's say it wasn't 3, it was 2, and this was 20. What we will do in our approach is that okay, we want x is equals to 3, so 20 minus 3, let's call it 21, okay, for easy calculation. So 21 minus 3 is 18, right? So we will leave 3 here and transfer 18 there. So 6 goes here and 12 goes here. Now, as you can see, after performing the operation on nth heap, we have 8 here and this much here, and then here we can see that we will be able to perform 6 plus 2, 8 minus 3. We will be able to transfer at maximum 5. Now because we want it always to be divisible by 3, we will just say 3, right? So we will say that okay, we will transfer 3 more, but this is actually not possible, because in the real order of operations is not hn to h3, it is h3 to hn. So we actually never received this contribution from h4. So that means that we cannot actually contribute this much. We can only contribute as much as we already had. So we will have to take the minimum of whatever our new value was, right? So h3, which was 8 minus 3, this is 5, and the minimum is 2, because since we have to go here first and then we will go to h4, we have to bound it by 2. And with this, we will always be able to tell if we can do these operations in such a manner that every value is at least greater than equals to x, and then we just binary search on this value x. So let me show you the implementation. Okay, so this is the implementation. I take the input, I have answer 0, low is the minimum value, that is 0, high is infinity. I do the binary search. So first of all, I copy the array A, I calculate the mid value, and can is just a flag that is initially true. Now I will perform the operations from n minus 1 to index 2 because it is 0 based, and then if at any point vi is less than mid, then obviously we cannot do. I'm breaking out, and then later on I will update can to be false. However, now I'm calculating the extra value, the extra that we can transfer. So extra we can transfer is vi minus mid, because we can transfer just everything else except mid, but we have to bound it by ai. Ai was the original values, and then we obviously divided by 3 to get the divisible, to get some value that is divisible by 3, because we want to divide it into 3 parts. And then I add extra to the index just before it, and 2 times extra to the index before it. And after doing all these operations, I iterate once again and check if any value is less than mid, then we were unsuccessful and we break out. If we were successful, then answer is equals to mid, and search space goes from mid plus 1 to high. Otherwise, search space becomes low to mid minus 1, and in the end just print answer. So binary search, I've noticed that is being used in a lot of problems these days, and this binary searching on answer especially. So you all should probably practice some binary search, and remember to subscribe. And with that said, bye. I hope I didn't FST any problem. And with that, I'll leave.